Okay, as we continue talking about nuclear physics, it's important to address how we refer to certain atoms or certain isotopes or certain elements. And we have a specific way of doing this. It's called Nuclide notation. And that's what the first part of this video is about. We're also going to talk about what is an isotope and some practical applications of isotopes and of nuclear radiation in general. So here's the idea of Nuclide notation. It's actually quite simple. This is what it looks like, right here or right here. So the first thing you do when you're trying to write a certain isotope, which we'll talk about what that is in a minute, but when you're trying to write down like a certain kind of atom with a certain number of neutrons and a certain number of protons, then the way you write it is as follows. First, you take the atomic symbol for that element. I'm doing carbon as an example, so the atomic symbol for carbon is just C. And then on the side here, you're going to write two numbers. The one that goes on the bottom here is the number of protons. The one that goes on the top here is the total number of nucleons. All right, so let's just take a look here really quick. What is a nucleon? Bam. A nucleon is any subatomic particle that's in the nucleus. In other words, protons and neutrons. So if we write the number of nucleons total, like so, that's going to be the sum of the protons plus neutrons. Okay? It's an interesting way of doing it. I'm not totally sure why they do it this way, but that's how they do it. So then, if you want to find out the total number of neutrons, then you're going to take this guy, subtract this guy, and that gives you the number of neutrons. So in carbon 12, as our example, there are 6 protons, bam, and there are 12 minus 6 neutrons. 6 neutrons. Right? So you just take 12, subtract 6, bam, that gives you 6 neutrons. Alright? Second example is carbon 14, which is a different isotope of carbon. It has a different number of neutrons. So in this case, still 6 protons, right? If you change the number of protons, you change the element. You cannot have an element that has a different number of protons. Say carbon always has 6 protons. Never 5, never 7. All right? 5 protons would be a totally different element. 7 protons would be a totally different element. Okay? So carbon always has 6, so that's 6. 14 refers to the total number of nucleons, so 14 minus 6 gives you 8 neutrons. So, bam. That's Nuclide notation. So you might be wondering, what is an isotope? Well, we'll just go through these definitions here really quick, and then move on. So an isotope is an isotope is a particular atom of an element that has a different number of neutrons than some other particular atom. So an isotope of an element has the same number of protons as any other isotope of that element, but each isotope has a different number of neutrons. Right? Different number of neutrons from other isotopes of the same atom. Alright, that's the key. That's the key definition of an isotope. Alright, it has a different number of neutrons from other isotopes of the same element. Alright, an isotope, a particular isotope can be stable or unstable. Carbon 12 is stable, carbon 14 is unstable. If they are unstable, then they are radioactive, and they will emit nuclear radiation of some variety, which is a topic for the next couple of videos. Alright, so how do we use isotopes? Well, there are several ways. First, they can be used medically, and basically because they emit nuclear radiation, we can see that, we can detect that with special detectors. So essentially, you can inject somebody with a radioactive element. Usually one that's not dangerous, right? They'll inject one that's relatively safe, not high energy. And then when it gets into your bloodstream or whatever organ they're trying to look at, I believe this is the thyroid in this case, in the guy's neck or girl's neck maybe, right there. That's the head, neck, right? So if you put the radioactive stuff in there, then you can take pictures of it and you can see where it goes. You can see sort of the internal structure of veins and so on. You can see where it collects. So radioactive isotopes are very useful for medical purposes, for scans and so on. All right, in industry, radioactive isotopes can be used for measuring the thickness of a metal that's being fabricated. So if you want to make sure that this metal sheet is all the same width the whole time, right? Say it's being rolled out into a sheet, and you want to make sure that the thickness of the sheet is uniform and constant. You can have a source of radiation here with good shielding all around it. The source of radiation is in there, and then there's an opening. So the radioactive nuclear radiation comes out through that opening. It's going to pass, some of it will pass through the sheet, some of it will be blocked. And then down here you've got a detector. So the thing's moving this way, here's the detector, here's the source of radiation. And basically the amount of radiation that's blocked by this sheet is directly proportional to the sheet's thickness. So if this starts getting more counts or starts getting less counts of radiation, then you know that this thing's getting either thicker or thinner. The thicker it gets, the less radiation gets through. The thinner it gets, the more radiation gets through. So you can tell based on how much radiation is coming through, how thick this is. Cool! Alright, here's another really common way that scientists try to use nuclear radiation. This one uses carbon-14, as well as some other radioactive isotopes that are in rocks and so on. So basically scientists think they can tell the age of something based on how much radioactive emissions there are coming from it. So for example, this fossil perhaps, if there's still some carbon in there, then scientists could basically take this to a lab, take a sample of it maybe to a lab, and then they measure the decay. How many counts per second, for example, are they getting of nuclear radiation? So if and then they think they're pretty sure they know the rate of decay of carbon-14, so then you basically just rewind the clock and you can try to determine how old that thing is. So here's just a graph of basically what carbon-14 looks like over time. On the bottom here would be the age of the sample in years, and then this would be the percent of carbon-14 atoms remaining. So there are several assumptions you have to make if you're trying to use this method. One of them is that you, based on the amount of carbon you have left, right, total, then you can sort of rewind and say when that thing was alive, it should have had a certain percentage of carbon-14 atoms in it. I'm not going to get into the whole thing. We can talk about this more in class. But anyways, they think they know, they think they can tell based on current state of this fossil, based on the current state of this fossil, they think they can tell how much carbon-14 should have been there when it was alive. So if they then know how much is there now, they can put it, like say 20% is left of what it originally started with, then basically follow the graph over, look down, somewhere around 12,000 years old is what that would be if there's 20% of the carbon-14 left in it. Alright, you'll notice that this method, carbon-14 dating, cannot be used for anything older than about, right there, 46,000 years or so. Doesn't work. There's none left. It all decays by the time you get to being that old. So anything older than this, carbon-14 is completely useless in dating it. Okay? Alright, last thing. that I wanted to mention is a smoke detector. If you guys have ever seen one of these things, probably in people's houses, maybe not so much in the Philippines, but they do exist, especially in the US. Every house has one, pretty much. This is what it looks like on the inside, and this is what it looks like on the outside. Notice, right here, let me zoom in on it. Warning! Radioactive material, americium-241. What is that? Well, it's a source of radiation, nuclear radiation. So there's a circuit, an electronic circuit going on in here, and it involves I'm not going to get into the details here because we haven't even talked about alpha, beta, and gamma radiation yet, but inside there's radioactive material, and when smoke gets in there, it basically it blocks the circuit, it sets off an alarm. We'll just simplify it that way. You don't need to know all the details of how it works. Just know that it does use a stream of radioactive particles as part of a circuit. So, there is yet another useful application of radioactive isotopes. Alright, so that's that. That's Nuclide notation, isotopes, and practical uses of them. I hope you found this helpful, and I will see you next time.